Hello, everyone. I'm Andrea Kropp. I'm a customer-facing data scientist at DataRobot, and I'm very happy to be here today to share a case study about extreme machine learning automation. So we've got a lot of content for you. We're actually going to kick off with some results. Then I'll talk about why we selected this case study and what are some of the transferable insights that I hope you'll take away. We'll go through the problem frame, look at the data set, cover the analytical approach, and then we do have a demonstration actually in the DataRobot software showing this methodology. That'll run about 15 minutes. It actually represents about 4 hours of elapsed time, which we've condensed down. And in that section, you'll see that extreme automation as we go through automated data preparation, automated feature engineering and reduction, automated model competitions, which some people call experimentation, and then the automated feature selection. So with that as introduction, let's get into the results. So the model we're going to take a look at did finish in the top 5% on Kaggle, right? That's not a winner, but it's not bad either out of 930 teams. And I should note that I am by no means a basketball expert, which you will immediately detect if you are a basketball analytics fan. The model we looked at also won us a little bit of money in Vegas. So one of our team members happened to be down at the Cosmopolitan. We placed a couple bets on a couple games in the first round. We bet on a few underdogs to win, not just cover the point spread, and we kind of tripled our money there. So with that said, you may be wondering, why is DataRobot paying data scientists to run around entering competitions and make money in Vegas? But that was really not our primary purpose. This all actually started with a hands-on experience that we were trying to offer to our own customers so that they could experience this extreme ML automation for themselves. We put together a lab experience complete with instructions and office hours, and we put all of the files up on Google Drive. And then we separated all of the entrants into coders and clickers. So our coders were kind of code-first data scientists working through our API, and the clickers were people who tended to be more the basketball fans who were just going to work through the graphical user interface. So what I'm going to take you through today is actually this challenge and basically how we ran it with the people who participated. Okay, so let's talk about transferable insights, and we'll stay on this slide for a little bit. So the first point here in blue, that automation is essential when time is, cut. All right, so let's talk about transferable insights. First point here in blue is that automation is really essential when time is short or machine learning backlogs are long. So the case we're going to look at here, time is short, right? Because the bracket is announced on Sunday night and the entries are due basically by Wednesday, right? The games kick off on Thursday, so time is short. But much more often in the corporate setting, the issue is that the backlogs are long. I actually used to run a large data science team where we spent at least 2 days every quarter deciding what we were going to say no to just because our backlog was so long. Point number 2 here in green is that your experimentation really should extend to include variations in data preparation. We see a lot of data science teams experimenting with different algorithms. So they might be trying an XGBoost, they might be trying a Keras model, but they often don't extend that experimentation to the data preparation phase. And then this becomes especially important when you're doing time-aware feature engineering or when you have a lot of text or image variables to be able to actually experiment how you're doing the text tokenization and featureization and how you're doing the featureization of the images. I already alluded to the point here in orange that dynamic time-aware feature search is going to be superior to building out feature stores. And I think you'll really see this in the demonstration. We will use automation to engineer over 1,000 features in the course of about an hour, but we don't know in advance which of those features are actually going to be useful to our problem, or we're going to throw most of them away. So building out a feature store in advance would have been a complete waste of effort. And the purple point here on feature selection by rank across many models is a new path to accuracy. I'm going to introduce you to a technique called feature importance rank ensembling, which might be something you have not seen before, which will give you some greater accuracy in your own projects. All right, so moving on to problem framing, there's really two ways we could approach this. We could focus on the use case itself in terms of, the focus is to develop a model to predict winners, or we could focus on the process. And for today, we're really focusing on the process. So how can we develop a process by which, ordinary basketball fans, as well as advanced data scientists, can experiment with many possible features, the feature lists, the data preparation methods, and do all of that modeling in kind of a 3-day period. So this is kind of the extreme automation. It's just kind of convenient that there's a lot of sports fans. So hopefully it'll also be a familiar data set. So let's take a look at the data set. The primary data set has over 100,000 rows, which represent over 65,000 basketball games. And in the primary data set, we need to have the target that we're predicting. So we're going to be predicting, does team 1 win the game? And in this case, we've got 2 columns to identify the teams. And every game identified by the ESPN number actually appears twice in the data set. And this will become important later. We've got a secondary data set here. Similarly, we've got each game appearing twice, and we have the actual in-game statistics or box scores for each team. So the 2 rows that are highlighted, the one on top is Tennessee's performance in that game, and the one on the bottom is going to be Texas A&M's performance in that game. Having looked at the data set, let's take a look at the analytical approach. So the demonstration we're going to focus on and the extreme automation really is in these first 2 stages. It's in the time-aware feature engineering and in the repeated autopilot and fire. And if you're not familiar with those terms, we'll explain them in a moment. After we use extreme automation across these first 2 stages, then we do some final blueprint tuning and creation of ensembles, but this will be out of scope for today. So the first step in the extreme automation is the time-aware feature engineering. We'll be linking that primary data set that you saw to the secondary data set twice. And we'll be creating some rolling statistics using 2-week, 4-week, and 6-week aggregations. So the resulting features will be things like the number of rebounds as a 2-week average, or the number of rebounds as a 2-week standard deviation, or the number of rebounds as a 4-week standard deviation. So at the end of this process, we'll have 1,700 new features. We'll reduce those down to about 1,400 that are informative enough to be retained. And all of this is going to be fully automated. Then we'll go through a process of DataRobot's autopilot combined with FIRE, where FIRE here stands for feature importance rank ensembling. So from the previous step, we'll have our 1,458 features. We'll hit the start button, and that will basically kick off our model competition. At the end of about an hour and a half or so, we'll have 70 models created. And at that point, we'll evaluate all of those kind of 1,000+ features to reduce them down to 279. Then we'll run the autopilot process again. We'll create 52 additional models, run the FIRE process again, reduce that down to 76 features, run autopilot again, add 48 different models. So this entire zigzag represents the automation and is controlled entirely through a notebook, which you'll see in the demonstration. Once we get down to this point, we'll be at about the 4-hour mark. And at that point, we can really apply some subject matter expertise and do some manual tuning toward our final model. So here's a deeper look at what is feature importance rank ensembling. I'll refer you to this excellent blog post. And actually, this image is not from today's data set, but is from this blog post. What we're doing here is trying out many, many different diverse models. So we might try some XGBoost, we might try some deep learning models, we might try some elastic nets. And then we're interested in calculating the feature importance for each feature across those diverse models and then ranking those from 1 to n. If we do that for enough models, we can actually then create a box plot of how each feature ranks to understand whether the feature is universally important across many different techniques or just happen to be important in a particular model. And then last step here, we won't spend too much time here on the tuning and creating ensembles. But what I want to draw your attention to is actually that our final ensemble winds up being a combination of model 581, 588, and 586. So the process we're demonstrating really is how did we get into model experiments in the 500s to be able to really narrow down on what was working to be able to create this final ensemble in the first place. All right, so I want to leave plenty of time for you to actually see the demonstration. This is going to be about 4 hours collapsed into 15 minutes. In this section, we will complete the automated time-aware feature engineering and the first round of autopilot. Before we hit the start button, let's take a look at some of the critical configurations. We'll be predicting whether Team 1 wins the game. The data we have loaded has a little less than 3,000 rows. This is just to make the demonstration run faster, and we will be comparing this to the full project that uses over 100,000 games. The number of features at this point is 10, many of which are redundant, such as the team ID and the team name. We have joined this secondary data set, and let's take a look at those relationships. So we've joined the primary data set to the secondary set based on Team 1 ID and Team 2's ID, and we'd like to prepare aggregations for 2 weeks, 4 weeks, and 6 weeks. In the settings area, we've defined which features and aggregations we want created. So we can go back to the project and kick off autopilot. I'm going to increase my workers to the maximum, and we're going to let the screen recording continue, and in the real version, we will fast forward until it's completed. Do take note of the time in the upper right corner. All right, it's about an hour and 20 minutes later, and autopilot has finished. And at this point, we have all of our engineered features, and we have 85 initial models. Let's take a look at some of the features. If you recall, initially we had just 10 features. Now we have well over 1,000, and we have them sorted by importance. We could also take a look at them by name. Each feature that has been created has complete feature lineage associated with it, showing which starting tables and which joins and operations were applied to produce that feature. Under feature discovery, we can learn more about the exact process of deriving these features. We can scroll through this log or we can download it. In addition to the log, we can also download the entire data set. At this point, we have far too many features and won't be using all of them. But this is also why we say that a feature store really isn't necessary. It would be a waste of effort to create a feature store with thousands of features, performing all of these aggregations in advance, knowing that we would probably reduce them down to less than 50 in the end. When we do sort the variables by importance, so far we're seeing a lot of the 6-week aggregations near the top, with the 6-week average win margin being one of the most informative features. I'm going to do some additional setup and take us over to a notebook environment before we start to analyze what's going on here in the Models tab. Stay tuned. In this section, we'll take a cursory look at the models that are currently at the top of our leaderboard, and then we'll switch over to a notebook environment to calculate the feature impact of different features across all of these models to be able to use the technique called feature impact rank ensembling, which will make more sense as we get deeper into it. At the moment, this gradient boosted greedy trees classifier is our top performing model. Here's the blueprint showing all of the pre-processing steps to prepare the data before the actual modeling takes place. The reason you'll see other gradient-boosted tree classifiers on the leaderboard is that the data preparation steps can vary. And so this is really a series of experiments combining different ways of preparing the data together with the modeling. For this particular model, the most important feature is whether Team 1 is playing home, away, or at a neutral location. The second most important feature is how many times Team 1 has won in the last 6 weeks. And the third most important feature is the field goal attempts that their opponents have taken as a 4-week standard deviation. Now, going back to all of these models on the leaderboard, they will have different feature importances. So we need to calculate the feature impact from all of these other models, and then we're interested in the rank of the feature impact. In the way that I went through 1, 2, and 3, we'll go ahead and calculate the ranks for all the features across the top models and then do some summary statistics. So let's do that in a notebook. So I've already connected to DataRobot, and I've already grabbed my project and listed these models. This list of top 5 from the leaderboard will match exactly with the graphical user interface. In this step, I'm going to kick off the feature impact calculations and create a data frame called all impact, which has the rank of each feature from the top 6 models. And also in this cell, we will take the all impact data frame and create an average impact data frame, which calculates the median, min, and max for each feature. Then we'll take a look at that data frame. So let's go ahead and execute this cell. When we do that, we'll actually be able to see that DataRobot has kicked off these calculations over here in individual containers. We can take a short break while we wait for these to calculate. All right, that task has completed. Let's go back to the notebook and get our summary. All right, so for each feature, we now have a minimum, maximum, and median rank across those top 6 models. And you may be wondering why that operation took so long to complete. In part, it's because the feature impact is calculated with something we call permutation importance, which basically reruns the entire model, just leaving that feature out, and looks at how much the model performance degrades. And then based on that degradation, it's able to rank the importance of the features based on how much worse the model gets if the feature is not present. In our summary table, we now have over 1,000 features, which is going to be too many for the final model. We can ask how many features do we have with a median rank of less than 100, and it looks like we have 121 of those. So we want to come up with some sort of rule of thumb to cut off the number of features we want to use and then rerun autopilot. So in this cell, we're going to say we'd like to keep features that are in the top 80 for at least one model, or has a median in the top 200 across all models. We're going to create a new feature list called top features, and we're going to ask that we rerun all of autopilot using those features. So we'll go ahead and pass this new list, and we will rerun the entire autopilot process. And we'll be able to go back over to the user interface to see some of that work kick off. So our second round of autopilot has finished, and you can see we've got some different types of model families here at the top. Now we're going to go back to the notebook, and we're going to run another round of feature importance rank ensembling, which will first require us to calculate the feature importance across the top 6 models. Then we'll reduce it down to hopefully less than 100 features, and we'll use autopilot one more time. Well, let's get the list of models. And we'll do the all impact and the average impact a second time. And that should kick off our feature impact calculations. And indeed, they are running. Where things stand after the second round of our Fire script has run. So we've got our average impact data frame, so we can see kind of the median across all of the features that remain. And then we did one final round of selection to say if a feature is in the top 20 for at least one model or has a median in the top 75 across models, then we want to run autopilot one more time, and that's what you see happening here. So going back over to the graphical user interface, everything is done now. We have our list sorted in order by log loss. And one thing to notice is that the models coming from the round 2 feature list are currently winning the competition. Here's a couple from the round 1 feature list. Here's one actually from the very first run with all of the features. But generally, as you reduce features, you will actually improve your model. It's just a challenge of knowing which features should you retain. So we're down to 76 features, having started from over 1,000. And we're not going to do it in today's demonstration, but typically at this point, you would select the list with kind of your remaining features. And you might do some additional reduction based on subject matter expertise. So I might select all of these features, rank them by name. Actually is easier to bring them together in kind of alphabetical order. And then I might say, okay, these are probably highly redundant with one another. Maybe I'll remove the 4-week count. And then here we've got a bunch of variables related to assists. I might say that the average and the median are probably redundant with one another, so I might keep just one of those. At this point, you could also apply some subject matter expertise. If there's anything here that just doesn't make sense to a subject matter expert, you could kick that out. Create a feature list. Now I might call this, manual 74 because I've removed 2 features. And then if I wanted to, I could rerun that entire autopilot using my manual feature list. Notice there's another mode here for comprehensive, which we have not yet tried. That would be another final step as you narrow in on your features to run comprehensive mode, which is going to try some additional pre-processing steps and some additional algorithms that were not part of pure autopilot. But if you take a look at the timestamp right now, have not been doing this continuously the whole time, but the CPU has been working most of this time, probably 75% of this time. So in the course of about 4 hours, we have engineered thousands of features, tried many, many models, done multiple rounds of feature reduction, and we're now in a very good state to apply some subject matter expertise to get down to those final models. If you recall, this was a short version of the demonstration with a little less than 3,000 data points. This is actually what the final one did look like. Let's go over to the data tab. Here you can see we started with well over 50,000 games, actually about 60,000 basketball games. And in our feature discovery, we decided to focus just on this 6-week time period. It might have been better if we used other time periods, but the more experimentation you do, the longer the run times are. And again, this was a timed contest where the bracket comes out on Sunday night and you need to have your entries ready a few days later. So on the Models tab here, there should be one with the star. Let me just use the filter here to find the starred model. This one, model 263, is the one that we actually entered in the Calgo competition and also used for the Las Vegas picks that I showed at the beginning. It has gone through 2 rounds of feature reduction, and then the final name of the feature list is AK picks, because we did go through and manually toss out features that didn't make sense or that seemed redundant. This was our final blueprint. We can take a look at the final list of features that were most impactful. And what I notice when I look at something like this is that, yes, the location is still the most important. Of course, the NCAA tournament is all played on neutral ground, but then there are many, many features that are all contributing 10% or more to the final prediction. And that will pretty much wrap up the time that we're going to spend actually in the software looking at how the case study was actually conducted. Welcome back, everyone. So let me recap some of the transferable insights from what you just saw. So number one, automation is essential. What you saw in 15 minutes was about 4 hours of elapsed time, but that 4 hours represents probably 3 to 4 weeks of work for an advanced data scientist. So that is a massive amount of cycle time compression, probably on the order of 100x. You should have also seen a lot of experimentation, not just in the modeling phase, but also in the data preparation phase and in the feature generation. You definitely experienced the time-aware feature engineering, and you saw how we could dynamically do aggregations on a rolling basis for 2, 4, and 6-week time periods, and then throw away the features we didn't need. This completely obviates the need to build out a feature store, and we'll be able to actually put this model in production just connecting to the original data sets without a feature store sitting in between. And you were introduced to feature importance rank ensembling. This might be a technique that you can use effectively in your own work, but again, it relies on that massive amount of experimentation. You need to actually try a lot of methods before you calculate the rank of each feature across those methods to make this technique possible. So thank you for attending today. If you'd like to try this yourself, like we said, this was a hands-on exercise. We can send you to the box folder. You can try this all yourself. There's lots more information on DataRobot.com about use cases in sports analytics, manufacturing, finance, education, government, and more. And of course, feel free to contact me at my email address. I'd be happy to take your questions and point you in the right direction. Thanks so much.